All right, good afternoon. We're really grateful for the opportunity to present today. We've worked the past month on this controller. We're excited to show with you what we have. So I know a lot of you have heard of Flappy Bird. It's an app that went viral just because it's very simple in nature, but it's actually very addictive and very frustrating at how complex the game is. So just to demonstrate that, for those of you who don't know, we've asked Kyle to come and play the game for us, just to show you how frustrating the game is. Kyle's really good. He's practiced all day for this. So this, what you're looking at right here, is we just downloaded a MATLAB code onto this. So this is just a version of Flappy Bird in MATLAB. Perfect control. Look at that. So the object of the game. So the object of the game is to navigate the bird through the tubes, and you do that by tapping each string.
It's my first day, guys.
Yeah, I got one. Okay, so how many of you played Flappy Bird before? Raise your hand. Okay, so who's gotten more than 10 ever? Okay. What about 20? I got 21. What about 50? Anyone got more than 50? Okay. So what's the highest score here?
Alan has no life.
148. So I was pretty proud when I got 52 until my brother let me know that he supposedly claims he had 430 taps. So I don't know if that's true or not, but so the object of our project today, or our project, was not only to beat my brother, but to just design a controller using process control to beat the average player.
Awesome. So in order to build a controller, we have to understand the physics, what is driving the game. So we went through a first principles model, and we verified this is actually the same physics equation that the game uses. So this simple physics equation relates position to an initial position, initial velocity, an acceleration term, and related to time. So to look at this controller, we look at it in deviation variables, and actually the Flappy Bird game evaluates this equation as a deviation in discrete time steps. So we're all kind of familiar with how programming works. It goes through a loop and it solves this equation for each small time step. So this helped us to get ideas of how to build our controller.
So our controller was essentially a proportional only controller. It had feedback and feed forward elements. The feedback element was that it measured the elevation and then compared that to the set point. And the feed forward aspect of the controller was that it could see the disturbances, the pipe elevations that were coming up. And there were essentially two parameters that we could change to tune our controller. The first was when the set point changed. So basically, as soon as you get out of the pipe, it would change to the next one, but you could make it change just a tad before that so it had more time, things like that. And the other parameter was the set point elevation. The set point wasn't exactly the average between the pipes, like exactly in the middle, because if we could adjust that, if we moved it lower, then there would be more room for jumping, and we wanted it to not run into the top of the pipe. So this next slide shows some of the data that we extracted from Simulink after running our model and in control. You can see the bands, those are the pipe gaps, and that orange line is the bird position. So you can see the flapping nature of the bird, and that light blue line in between the gaps is the set point. You see how that's a little bit below so that it has space to jump and still not run into the upper bound. And that gray function on top is the error. So basically, whenever the error was positive, the controller would tell the bird to flap until the error was negative, and then it would stop flapping until it became positive again. So we'd like to demonstrate to you what our controller looks like, how it does.
There goes.
Oh, it's still going, don't worry.
Wow. So you can keep watching while we talk.
So this controller isn't perfect. It's a P-only controller, and so it has some inherent weaknesses. And one of those is that when there's a large change of gaps between the pipe from high to low, if the jumping phase or if the jumping frequency is off just a little bit, then it'll actually run into the top pipe and crash. So in order to overcome this, we would need to incorporate a predictive model into the controller. But as you can see, it does pretty well for just about every change that it's given. But yeah, in summary, we built a controller that is better than the average human player with a high score of 703 and an average of several test runs of 139. And so we did beat the game creator's high score of 150 and Trevor's brother at 423. And it's, yeah, so that's what we did. Thank you for listening.